Hello everybody, my name is Bartl. I'm from the PTV in Germany, which is the National Metrology Institute there. And my rather longish title I'd like to condense to more significant words. So what we are working at PTV on is the full field precision interferometry for measuring length. And from the length we can also determine strain and thermal expansion. But fortunately, in this long title, also my outline is hidden, because I want to introduce you into the basics of this type of interferometry which we are applying. Paul told you already a little bit about the basic principle. And what we are also doing is varying the temperature in order to determine the coefficient of thermal expansion of different materials. And in the scope of this METCO project, we developed the equipment for also varying an electric field in order to determine the expansion of length of piezoelectric materials. So first of all, what is the motivation for us? Well, as I told you, we are the National Metrology Institute of Germany, and one of our legal duties is the dissemination of the basic unit of length, the meter, and that means that we are providing scientific and technical services in this area. And in our department we are applying interferometry for the determination of the absolute length of material measures. For instance, you see here these gauge blocks which are used for length comparisons or calibration in industry. These are made of different materials. For industry, very often made of steel, or for very precise applications in science, also silicon material. This one is a different material, ceramic. And as I already said, once we have the absolute length of such a body, we can derive the coefficient of thermal expansion or the compressibility due to a variation of the surrounding pressure of air. And we can also survey the long-term stability of these materials after a certain treatment, temperature change or whatever you can imagine. And all this data can be used for the calibration of material measures, and it is a characterization of material properties, and this is the role, this is our role in the METCO project. You have this triangle of coupling effects in piezoelectric materials, and these two are under investigation in our experiments. So we are varying the temperature and also the electric field applied to the sample and determine the mechanical change of length of these material samples. You have seen these samples already in the previous talk, and what we are exactly doing is, in the full field of view, the investigation of the length change or change of the topography of these samples at temperatures between room temperatures up to 200 degrees centigrade, and with an electric field applied in the range from minus to plus 2 kV per millimeter. The basic principle in our experiment works as follows. You can think of using a wavelength as some kind of a ruler to determine the length of such a material measure. The length is then expressed as a multiple of a well-known optical wavelength, which directly relates to the definition of the SI unit meter. So we use such an interferometer. Paul already showed you a sketch of this thing, but the main difference is that in his setup at NPL they use a laser, a point source from a laser, and we are using also a laser as a light source, but the laser light is divergent and then collimated, so that we are illuminating the sample under test in the whole field of view of the optics. The rest is similar to the setup which Paul has shown you in his talk, and the length can then be defined as it is stated over there, as a multiple of half the wavelength multiplied by the sum of an integral and a fractional order of interference. So what we are determining is this gap here in this simulated interferogram, the gap between the interference pattern on the surface of the sample body and the surface of the reference plate on which the sample under test is located. This integral order of interference can be derived from different types of measurements, or in our case by using multiple wavelengths, different wavelengths. There's a special technique called method of exact fractions, and this can be used to in a certain range of length to determine this integral order of interference. And as I already showed here in this picture, the fractional order is directly derived from these interference patterns. There are, of course, some limitations. First of all, I have there the quality of the optical components, because, for instance, variations of the refractive index in the material of this beam splitter, for example, directly has an influence on the appearance of this interference pattern, and then we see this influence in the result of the length measurements. And also the alignment and quality of the optical wavefronts is, of course, an influence which has to be taken into account, because if you have a tilted wavefront, this also has an influence of this on this interference pattern, and reduces the accuracy of the measurements, for example. The same is for the parasitic interferences, which might be introduced by multiple reflections between several optical components in this light part in the interferometer. This all belongs to the sample requirements. Paul has told you some words about that. Due to the fact that the beam path is rather long, we have very strict requirements for the parallelism, because otherwise, in the extreme case, the reflected light from the sample does not achieve the camera, so we don't get any signal from the measurement. Beside all these optical limitations, there are other limitations. For instance, the temperature measurement is very important. You may imagine that each temperature change directly has an influence on the length which we are measuring. That means we have to measure the temperature very precisely, depending on what uncertainty we are aiming at for the length measurement. Similar, the index of refraction, if we are not working in vacuum, Paul already said that it's also a restriction for the uncertainty of the measurement, and the accuracy is reduced if you cannot determine the refractive index of air very precisely. Then we have also the temporal stability, which is also linked to temperature measurements. For example, if you are performing measurements over a longer time and you cannot make sure that the temperature is stable enough, then all this enters the result of the measurement. Well, the principle of the length determination works as follows. Here you see a photo of such gauge block shaped sample arrangement. There are different bodies on this reference plate. This is some type of ceramic. I don't know what exactly it was. First of all is the acquisition of phase shifted intensity frames. Here you see the series of shifted interferograms. As you can see, these fringes are moving. That just means that the surfaces of these sample bodies are tilted slightly with regard to the surface of the reference plate below them. The next step then is the evaluation of the phase map, which gives you the information about the height variation of the samples with regard to the reference plate. Then you can calculate, like it is depicted here, the phase difference between one of these sample bodies and the reference plate directly in the surrounding area of the body under investigation. And this phase difference gives you the fractional index, the fractional order of interference, which we are looking at for the determination of length. And then you finally can calculate the length by this formula. And as I told you, you have to determine the integral order of interference by another way, or by using multiple wavelengths. Once you have such a length value, you can vary one of the parameters, like the temperature, for example, and you can repeat these length measurements. Then you get such a plot. This is just simulated data. It's not real data, but you can follow the length change and calculate, for example, if you vary the temperature, the coefficient of thermal expansion for a material under test. But for the netbook project, it's more important not to have a look at the thermal expansion, but the variation of another quantity, for example, the voltage applied to such a sample disk. This is pz on an aluminum nitride reference plate with a gold pattern on the surface as for the contact of the lower electrode, which is coated on the sample surface. And you can do the same, for example, for the piezoelectric expansion, the D33, for example. This is a sketch of our real setup. As I told you, we use several wavelengths, in this case 3 lasers with these wavelengths. All these lasers can be coupled into a fiber, so that the light coming out of the fiber is collimated, enters the vacuum chamber, which is 2 meters in diameter. The light is split in 2 beam paths, the reference path and the object beam path, where the samples under test can be located, and on the way back both beam paths are collected and then yield this interferogram pattern on the camera. This setup is called Twyman Green interferometer, which is different from the setup which Paul has shown you, as we are using this collimated beam path to illuminate the whole sample under test and not only at distinct points. The measurement uncertainty which we can achieve with this setup under optimal conditions is in the order of 1 nanometer. But unfortunately, and I'll tell you more about that in a few minutes, we cannot achieve this very low uncertainty for the piezoelectric measurements due to several conditions. Well, as I told you, we perform imaging of the entire sample surface and apply a phase shifting technique for the determination of these phase maps for the length variation. Currently we are applying different configurations of the setup. The first one is for ambient temperatures inside the main chamber. This is what you have seen on the slide before. Here we have this translation stage for several samples. But we also have an external measurement path outside the actual vacuum chamber for measuring at cryogenic temperatures. In this external measurement module we can reduce the temperature down to 7 Kelvin and measure up to ambient temperatures. And for the METCO project we developed a new special module for higher temperatures and the application of high voltage. This is something which we could not do before, and therefore we added a further mirror in the vacuum chamber to add this high temperature module inside the vacuum chamber. This is how it looks like in reality. This is the sample holder here on the left, in the left picture. In the center you see a heating module, and on the top of this heating module you have the reference plate and the sample under test, which can be contacted for the application of the electric field via these gold-coated levers. And on the top of the reference plate you also see this gold pattern for the contact to the lower electrode of the sample. Then we add this gold-coated shield in order to protect the surrounding optics inside the vacuum chamber from the heat radiation. And if we take a closer look to the center of the setup, you see also here this small hole inside the reference inside the reference plate. As I told you, temperature measurement is very important for these length measurements, especially in the case if the material under test has a large coefficient of thermal expansion. Unfortunately, we are only able to measure the temperature inside the reference plate and not directly on the sample under test, which would be better, of course. There will be a gradient in this temperature measurement or in this sample arrangement, and we were able to measure that this gradient is less than 5 Kelvin, but as long as we cannot measure it more precisely, we have this systematic uncertainty contribution, which is one of the largest at the moment. The measurement procedure for the application of high voltage works as follows. At a given temperature, we vary the voltage step by step over time, and at each plateau of the voltage, we perform this acquisition of interference images, which takes about 1 minute or slightly more, so that we can then evaluate the length variation across the whole sample. Of course, not only the sample, but also the reference plate. And now I show you some exemplary results. First of all, the surface deformation, which is special for our setup because this cannot be detected in the German interferometer, as this type of interferometer only detects pointwise deformations. This image shows you the sample surface at the beginning of the measurement. The tilt is subtracted to see the real surface variation. And then we go step by step through the voltage up to 4 kV. You see that the surface shape changes slightly, and when we go back to 0 volts, it looks a little bit different than at the initial state. Then we go down to -4 kV, the surface changes, and after the whole cycle of the voltage, you see that after switching off the voltage, the sample surface, well actually I'm not sure if you can see it really because the contrast is rather bad here on the screen. But what I wanted to show you is that the surface shape looks a little bit different than compared to the initial state, and after 30 minutes it still changed a little bit, and this can be continued over a certain time until we reach this initial state again. And this was done at room temperature. If we now focus on the first positive polarity branch, we have taken lots of surface images, and if you have a look at such cross sections through the sample surface shape, you can see with increasing voltage that the length changes. Mainly it's a piston type movement, but what you can also see that the shape shows a slight bending compared to the initial state. And this can also be done for all the other voltage parts. This is just an example to see what we can do with this global imaging of the surface. More familiar for you may be the following. If we have a look not to this surface images and not to these cross sections, we can also evaluate the data in a way that it looks like such a bipolar loop. All these data points are evaluated as the surface average length change of the sample. And as you can see in this sketch, we increased the voltage, went down to -4 kV and then back to 0. And what came out for this positive branch here is this value for the D33 of the sample. It's only calculated for the positive part, and compared to the technical data value, it's in a good agreement with this. We also have done this at higher temperature, in this case only at 100 degrees centigrade for a test of our setup. This is again such a bipolar loop at 100 degrees. The sample looks slightly different than at room temperature, so just the change of the temperature already changed the surface of the sample, and then we see a larger effect compared to the room temperature measurement on the surface deformation. And the most important thing is that at negative voltages, in this case around -2 kV as far as I remember, the surface changed dramatically and stayed in this state. You see these local deformations which do not disappear when we remove the voltage again, and even after 3 hours after switching off the electric field, the surface still remains in this state. So we detected severe changes in the absolute length and also the topography of the sample, and this was irreversible, and we had no relaxation to the initial state of the, before the measurement. Looking at the picture of the bipolar loop, well, it's similar to the room temperature measurement, only that in this case you see that the increasing branch and the decreasing branch of the positive voltage are split slightly more than before, and as I told you, around -2 kV or -2.5 kV, the sample broke obviously, so that all these data below -2 kV are not reliable. Sample destructed. Finally, let me summarize our key achievements. We could extend the experimental capabilities of our interferometer to high temperatures and also high voltage. And we tested the new equipment successfully. It works. Unfortunately, we also destructed several samples. And if you have now some questions, I'm happy to answer them. Thank you.